So here's one question that's been haunting the dreams of theoretical physicists for the past 40 years or so, at least since Hawking published this paper back in '76. Do black holes evolve pure states into mixed states? Well, we know that in ordinary quantum mechanics, time evolution is unitary. So if we start with a pure state, denoted by a density matrix whose trace of the square is equal to 1, and if you evolve it with a unitary operator, then the trace of the square of the final density matrix is going to be still 1. So in this sense, in ordinary quantum mechanics, purity is eternal. In this paper, Hawking suggested that perhaps in quantum evolution of black holes, or quantum effects on a black hole spacetime, you could have some sort of evolution of a pure state into a mixed state. And in order to realize this, he proposed that instead of having an ordinary unitary operator, there must be, or there could be, a superscattering operator which allows the evolution of initial pure state into a final mixed state, so state for which trace of rho squared is less than 1. Well, over the years, this initial proposal of Hawking has actually fallen into oblivion. There are some notable exceptions today that still advocate some fundamental loss of unitarity, namely Bob Wold and Bill Unruh. But for most of the community, all efforts in the past 20 years have been directed into try to find a way in which you could have a unitary evolution of black holes while evaporating. Why? Why this idea of fundamental decoherence has fallen into oblivion? Why people have looked into all possible ways of recovering information? Well, the culprit is this paper that appeared in 1984 by Banks, Peskin, and Susskind. And what they did in this paper, they actually built up on a previous paper by Ellis, Aglayanopoulos, and Srednitsky, and they studied the dynamics associated with this superscattering operator, just looking at some differential form of this superscattering evolution. And they looked at differential time evolution for the density matrix in terms of this H/ operator, which is not equal to the usual commutator between the Hamiltonian and the density matrix. And the original proposal of these guys was just to look for possible phenomenological signatures for this departure from unitarity that Hawking proposed. So Banks, Peskin, and Susskind looked for a general form for this H/ operator, requiring two basic properties: that hermiticity and trace of the density matrix should be preserved during this generalized time evolution. What they did in their paper, they rediscovered what was already known by some people studying evolution in open quantum system, and this equation is called the Lynnwood equation. So you have the ordinary term here, time evolution, plus some term that's known as a decoherence term. And their conclusions at the time, 1984, were lapidary. So looked for a more general evolution than the Schrödinger equation, and we argued that any more general equation for rho violates either locality or energy momentum conservation. Tomb on this thing. Nobody looked at this any longer. Besides, about 10 years later, one of the original guys from the Ellis paper, Srednitsky, looked at the problem again and actually observed that the kind of non-locality which Banks, Peskin, and Susskind were arguing in the original paper was there if you have some generalized time evolution is actually harmless, because it does not lead to any macroscopic violations of locality. But the problem that he found then in 1993 was that he could not realize a covariant version of this Lynnwood equation. So he assumed that you can conserve energy, but he could not find a reliable covariant equation. The only equation he studied led to development of negative eigenvalues for the density matrix, so problems with probability. And also he had the philosophical worry that one may still question whether or not this Lynnwood equation has any reasonable chance to arise at the low energy limit of some more fundamental theory. I know of no such theory. That was the conclusion at the time. And so he finished the paper with this nice sentence: the fascinating possibility that purity may not be eternal is still out of reach. Well, the point of this short talk, the point I will try to make is that Planck scale deformations of translation, in a sense that I will illustrate soon, naturally allow the possibility for generalized time evolution. Okay? So this is the plan of the talk. Let me start with a tribute to Max Born. We are here in Platz Maxa Borna, Max Born Square. And it was actually Max Born that in this paper in 1938 first proposed that actually curving in some way momentum space could give us some good hints towards our journey to quantum gravity. And in some way here, the starting point of my talk is the idea of Born reciprocity in phase space. In which sense? Well, it is well known that there are classical systems which have a phase space of this form, where coordinates belong to a non-abelian Lie group, and momenta just belong to ordinary Minkowski space. For example, the isotropic rotor. So, by Born reciprocity, we would expect that there should be some classical systems in which phase space is of the reciprocal form, where actually momenta belong to some non-abelian group. Do these classical systems exist? The answer is yes. This was realized about 60 years after the original work of Born. This was actually a work that built up on previous work. And you have classical systems which are particles coupled to gravity in 2+1 dimensions, which actually exhibit this type of phase space. And let me show you how this arises. So GR in 2+1 dimensions admits no local degrees of freedom. The way you can couple particles to the theory is just adding defects, space-time defects. And the resulting geometry is just a conical geometry. This was shown in the seminal paper by Desert, Jagiv, and Toft, 1984. So you have a cone, and you take spatial sections of this geometry, and you have this conical space with density angle is proportional to the particle's mass. And you can actually realize this proportionality in 2+1 dimensions because Newton's constant has dimensions of inverse mass. Okay, so this is the deficit angle of your conical space-time, and the mass is proportional to the deficit angle. So you can actually calculate the mass of the particle at rest by taking the holonomy of the flat connection around the defect, and you will see that this holonomy turns out to be a rotation by an angle alpha. So the particle's rest energy is represented by a rotation, by an element of the Lorentz group in 3 dimensions. So if you look at the ordinary idealistic kinematics, now switch off Newton's constant, you have this nice isomorphism between Minkowski space and SL2R Lie algebra as vector spaces, and you can actually see that you can represent momenta in terms of 2x2 traceless matrices in this way, and the determinant of this matrix just gives you the mass shell condition. And then you actually see that if you act with the matrix representation of SL2R on its Lie algebra, this action preserves the determinant. So from the rest momentum, okay, the rest energy, m gamma naught, you can Lorentz transform, boost and rotate to create any momentum, any physical momentum on the shell. Okay? Okay, so, and this momenta just belong to this physical momenta belong to orbits of the Lorentz group on the Lie algebra. Now, what happens when we switch on gravity? We just saw that the rest energy vector of the original relativistic kinematics now becomes a group element, rotation by an angle alpha. Okay, so in some way you exponentiate this vector element of the Lie algebra to a group element. Okay? And then, in analogy with the ordinary case, what you do to produce all physical momenta, you just boost the rest energy. And so you have that physical momenta are obtained by conjugation of this rest momentum. So physical momenta are elements of what are called conjugacy classes of rotations by a given angle. The angle is a definite angle which is proportional to the mass. So you label these deformed mass shells by the mass of the particle or by the original definite angle. And as in the, let me call it at the undeformed case, the G equals 0 case, mass shells are given by the determinant of this vector space element. Now we have these deformed mass shells which are given by the trace of this physical group element which represents momentum. Okay, because trace is preserved under conjugation while determinant was preserved under a joint action of SL2R. All right, so this is the main message. In 3 dimensions, when we couple particles to gravity, we have that momenta are parameterized by group elements, elements of SL2R. You can actually see this from a geometric point of view. You can just take your static conical geometry and you boost it. The same way you do the Eichelburg-Sechsel boost. And you will see, once you have the boosted geometry, you calculate the allonomy, and what you get is an element of the conjugacy class of rotations. This picture can be generalized to higher dimensions. We did it with Tomac, our paper, and to massless defects. If you look at massless defects, then you will have conjugacy classes of null rotations instead of rotations. And actually, something interesting is that Toft used these defects, conical defects in higher dimension to construct his model of piecewise flat gravity back in 2008. But anyway, let's look a little bit closer at the properties of these SL2R momentum spaces. Let me parameterize elements of SL2R by 2x2 traceless matrices and identity matrix here. And let me denote the inverse Newton's constant multiplied by 4 pi with kappa. Then the unit determinant condition reads like this, which is nothing but the equation for anti-de Sitter space in 3 dimensions. So we have that momentum space becomes anti-de Sitter space. It's no longer Minkowski space. And these p coordinates are just embedding coordinates for this space. Then you can actually write down explicitly the mass shell condition. And this is nothing but the ordinary mass shell condition with a renormalized mass, which I called m kappa. And you actually look at the way Lorentz transformations act on these coordinates on SL2R. And for the case of these embedding coordinates, the action of a boost, for example, in the gamma 2 direction is just the ordinary boost. Okay? Now, very important question. Can we play soccer on a non-abelian momentum space? These, the connoisseurs of these models acknowledge that there is a very important problem which is dubbed the soccer ball problem, which says, well, if you have this group valued momenta, then how, if you have these deformed kinematics in the real world, if this should be taken as real kinematics, then how would you deal with the classical particle macroscopic objects and so on and so forth? Well, let's look at what happens at this classical. So we have this phase space of this form. So we have 3D Minkowski space-time SL2R. So let's ask the question, what about total momentum of composite systems? Well, we know that for classical systems, an observable is just a map from phase space to the reals. Particular, for momentum associates to each point in phase space a 4 vector. Okay? So if we look at the composite system, classical mechanics, we just take the Cartesian product of the individual phase spaces. Now, we know that there is a non-trivial group law on, let's say, the momentum portion of phase space. Okay, let me call it gamma pi. And this is non-abelian group law. This non-abelian group law induces a group law on the Cartesian product of the momentum spaces, okay? So we have these ordered pairs, and this is the group law on the Cartesian product. In particular, any point belonging to the Cartesian product of momentum spaces can be written as multiplication of these elements of the Cartesian product. And look, the non-abelian group law restricted to this kind of elements is abelian indeed. Now, we know very well how to define a non-abelian addition of 4 vectors via group homomorphism for this composition of momenta. So if we look at the momentum carried by this element here, we see that this non-abelian addition, for exactly this reason, reduces to an abelian addition of basically individual momenta, since we have the isomorphism between this gamma pi 1 and the identity element. Okay, so at the classical level, the total momentum of the system reduces to an abelian addition of individual momenta of the single system. At the quantum level, the situation is radically different, because now you have one particle spaces, one particle Hilbert spaces, which are spanned by cats labeled by group elements. These cats admit a plane wave representation in terms of non-commutative plane waves. Okay, non-commutative because you have to introduce a multiplication rule here, which complies with the non-abelian group structure. So if I'm multiplying 2 plane waves, e pi 1x, e pi 2x, this multiplication must be non-abelian, since the resulting plane wave will have as an argument pi 1, pi 2. And pi 1, pi 2 is different than pi 2, pi 1. Now, in this case, the 4 momentum observable associates 4 vectors to the eigenstates, to these eigencats. Okay, so I will associate some coordinates p mu over on the element of the group. So if I take a 2-particle state, which is now given by the tensor product of Hilbert spaces, the wave function representation, the plane wave representation, will be given by a star product of 2 plane waves. So by definition of momentum observable, this guy will bring down the coordinates of the group element pi 1, pi 2, which we showed in the previous slide, is just given by group homomorphism by a non-abelian addition. Okay, so in a quantum case, momenta do sum up in a non-abelian way. To illustrate further the consequences of these facts at the quantum kinematical level, let me recall some basic representation theory. So we just saw that the basis of eigenstates can be taken as eigenvectors of the translation generators. This is ordinary theory. Then we know how to define an action on the dual Hilbert space. This is just the dual representation of a Lie algebra. In this case, the Lie algebra, well, of the Poincaré group or the subgroup of translations. And this action on the dual space is given by this. Okay, it gives you minus the eigenvalue when acting to the left. And let me call this action to the on the dual space with this index. So this is equal to the action to the left on cats. I define it as the action to the right of something which I call the antipode of the symmetry generator. Also, on composite states, on states of composite systems, I know how to define the action. The action is like a derivative. First I act on the first, then I act on the second. And let me call this kind of action with this delta p mu, which I call the coproduct. These are basic off-algebra notions built in ordinary quantum field theory when we do ordinary quantum field theory, okay? So this is the antipode minus of p mu, and this is the coproduct. First I act on the first, then I act on the second. What is very interesting is that these basic notions of Hopf algebra theory are actually sufficient to derive the action of p mu on a generic operator. Take, for example, the simplest operator, the projection operator on some ket k. Then what I do when I act with p mu, I'm acting essentially on a tensor, on an exterior product. So I first act on the first, and I then act on the second. But when I'm acting on the second, I'm acting on a bra. So I have to have the minus. So this reproduces just the ordinary adjoint action of translation generators on operators. And by the spectral theorem, I know that I can use these projectors to reconstruct any other operator. So this will give me the adjoint action of p mu on any operator. Now, the basic point is that when our momenta are group valued, these basic notions are changed. Now we have kets which are labeled by elements of a non-abelian Lie group. And so I associate as observable some coordinates on this Lie group, pi mu. Now, already for the action on the dual space, or the action on bras, the non-trivial structural momentum space comes into play. Now this observable is not reading the coordinates of the group element pi, but is reading the coordinates of the inverse group element, pi minus 1. And at the same time, the actual multiparticle space now, as I showed before, is reading the coordinates of this group element, pi 1 combined non-abelian in an abelian way with pi 2. And this is, again, some coproduct which is non-trivial, since the composition of momenta now is non-abelian. And this, in fact, is reflected also in the fact that I should have a non-trivial, let's say, antipode, because you have a non-abelian composition here with the inverse group element, which should give you 0, as in ordinary case. So in Hopf algebraic language, I have a non-trivial coproduct and antipode. So the key point, the whole story, boils down to the fact that if I have a deformed, a non-trivial coproduct and antipode, the action on operators of these similar generators will be changed. In which way? Let's look at it. So for the 3D gravity example, things are very simple. We just have a trivial ordinary antipode and the coproduct a leading order in the Newton's constant. Remember, kappa contains inverse Newton's constant. Reads like this, okay? So I have the ordinary Leibniz action plus this term, which is essentially a wedge product in 3 dimensions. So I can just go on, and like in the previous slide, calculate the adjoint action of the translation generator on a generic operator. As a generic operator, let me take rho, density matrix. And the result is this, which can be recast, very nice form of a Lynnwood equation. Okay, so I have the ordinary term plus the coherence term, where this decoherence matrix here, you see, is inversely proportional to kappa, which means that when g goes to 0, this term disappears, and I have ordinary time evolution. But when gravity is switched on, my evolution is Lynnwood type. Okay. Now, let me have a closer look at this. Yes. Yeah. Ordinary, yes. Yes. That's a good question, yeah. Well, no, because should be done. That's actually the remarks I'm going to make later. So let's. So let me look at this decoherence term, okay? Because we know all the history of this Lynnwood equation was discarded back then, right? So what's happening here? Why do I have? So let's see. Why do I have a Lynnwood equation which is actually covariant? Srednitsky told me that there is no way to have a Lynnwood evolution which preserves energy. So let's remember that Lynnwood evolution preserves energy if the operators in the decoherence term commute with P0. Okay? In this case, they do. These are space translations here. They commute. These guys, the P's are just commutative, as usual. No. In the computation rules of the P's, there is no. All right. So we know that Lynnwood evolution preserves trace and hermeticity by construction. Okay. So we are happy with that. But there is an important caveat. Conservation of positivity of the density matrix is not guaranteed. So what Banks, Peskin, and Susskind showed is that if you have H matrix, positive definite, then positivity of the density matrix during Lynnwood evolution is guaranteed. But they were not able to prove any more general results. Okay, it's very hard. What they also showed is that H matrix is real, so has real entries, then the entropy increases, the von Neumann entropy associated to the density matrix increases in the Lynnwood evolution, which is what you want if you want to deal with the information loss issues. And then, as I said, energy is conserved if operators in the coherence term commute with P0. So Srinici told us that the requirement of energy conservation is not compatible with covariance, but we just seeing that that's not true. What's going wrong here? Well, what is going on here is that both Banks, Peskin, and Susskind, and Srinici, because of these reasons, restricted to real and positive definite decoherence matrices. And now we see that instead in this gravity scenario, we have a natural, well, we derive the decoherence matrix which is nor positive definite, not positive definite, nor real. So, as you said, now what do you do? Well, you should work out and see if this gives you problems, if there's some physical negative eigenvalues of the density matrix developing. So it's all stuff to be done, actually. So, how much time do you have? More or less? 15? No, 10. No, I'm just simply showing that there are some theoretical frameworks actually linked to gravity. This is in the 3D case. Now I'm going to the 4D case. This is what I did was just for a point particle coupled to topological gravity in 3D. Okay? So I look at the phase space of this particle. I quantize the particle. The particle has these non-trivial features. And the non-trivial feature is that the time translation generator acts in a way which reproduces the Lynnwood equation, which was thought to be very pathological and also with no relationship with any theory at all. I'm showing here that it has actually relationship with gravity, at least in 3D. And well, these are points of view. I mean, from my point of view. From my point of view, what you're changing here is the phase space structure. Just looking at the phase space. Gravity is just ordinary gravity, not quantizing anything. You're just quantizing a deformed phase space. I disagree. Sorry, Laurent, but anyway. Okay. Anyway, so let me just conclude with a few slides about the generalization of this picture to 4D. Can we generalize this group-valued momenta to 4D? Yes. There is a model which was formulated back in the 90s by Professor Lugierski and collaborators here in Wroclaw. This is called the Kappa-Poincare algebra. And essentially, these have very similar features to what I just described in the 3D case. In this case, you have that momenta are coordinates on a non-abelian group. And instead of SL2R, now you have this four-dimensional non-abelian group, which is called AN3, which can be obtained by factorizing the five-dimensional Lorentz group in this way. And you can see that this Lie group as a manifold is just half of the de Sitter space. And here they say the cosmological constant of this de Sitter space is related to this deformation parameter, which I call kappa. Well, in this case, you have also a non-trivial coproduct and this time also an antipode, which is non-trivial. So we have deformed, let's say, Leibniz action. And, well, for these guys, you can see that the action of the Lorentz transformations on these coordinates on this portion of the Sitter space is just undeformed. And you have also a mass shell condition which is undeformed. So the only non-trivial structure appears in this representation theoretic information that you have in the coproduct and the antipode. So you can do the same calculation. Go ahead, look at the adjoint action of the translation generators. And this time you get something a little stranger than ordinary Lindblad evolution. Compared to the 3D gravity case, you would expect an extra p vector squared times rho, right? Which is what you need when you take in the Hermitian adjoint of this guy, right? Why do you have this form? Well, because in this case we have a non-trivial antipode. The non-trivial antipode enters in the definition of the Hermitian adjoint. So when you're taking the dagger of some adjoint action, this is equivalent to the adjoint action of the antipode. Think about the ordinary commutator. When you're taking the dagger of the commutator, if your operators are Hermitian, you're just flipping the sign. If you have a non-trivial antipode, then you have to take into account this. And this is what causes you to lose a term here. So you have this form of, say, non-symmetric Lynnwood equation. Also, about covariance. While in the 3D case, we had ordinary action of Lorentz boosts, now the adjoint action of Lorentz boosts is deformed, because also Lorentz boosts have non-trivial coproduct and antipode. And so this equation complies with the deformed notion of covariance, okay, which is this one. Okay. All right. So to summarize, what I try to show or try to convince you is that models of quantum kinematics with group-valued momenta and associated deformed translation generator provide a natural framework for some fundamental departures from ordinary time evolution. I'm not saying here that we are violating unitarity, I'm just saying it's a type of time evolution which generalizes the usual von Neumann time evolution in quantum mechanics. In 3D gravity, this is due to the topological nature of particles in the theory. So the energy and momentum become topological charges, become group elements. And the remarkable thing, which I think is remarkable, is that in 3D, your decoherence term is proportional to Newton's constant. When you switch off gravity, when you put g equals 0, that disappears, you obtain ordinary time evolution. And I also showed you that we have some 4D models for which this can be realized. The connection with gravity is a little bit more, well, let's say, there's no connection with gravity, but it's a model, it's there, and it's been studied over the years. And it has some interesting properties because we don't really recover a Lynnwood equation, but some mutant form of Lynnwood equation. Well, what's next? Well, a lot of things. So, first of all, is this kind of generalized time evolution physically acceptable? Does it lead to, for example, negative eigenvalues for density matrix, so problems with probability interpretation of density matrix? Well, if it does, then it's good news and bad news at the same time. And if it does not, it's good news and bad news at the same time. Why? So, if this is not physically acceptable, then you can throw away everything. You say, okay, fine. This is not physically acceptable. If it is physically acceptable, then it's interesting. Well, the other question is that what is the fate of unitarity? Are we talking about theories which actually violate unitarity in some way, or are changing the notion of unitarity in a way which allows pure states to evolve into mixed states. Of course, then, what role these things could have for the coevolution, this is natural. But then the other interesting thing is that after the paper of Ellis et al., there was a whole literature which developed about looking for phenomenological signatures of these departures from ordinary von Neumann evolution, especially using neutral count systems, where there's super high sensitivities. So the natural question is that can we actually put bound on this kappa that we have in the 4D models using these measurements? Okay, and actually in Rome we have these measurements being made at the Frascati laboratories with the Chloe 2 experiment with these neutral counts. So that's it. Thank you very much.
So have you looked at these papers by Weinberg? The recent couple years has been on, in his own way, playing with generalized equations for the density matrix, partially being motivated by decoherence or measurement problem. I don't think he believes in decoherence now, but and they are Limblund-like, but they're more general.
I'm not aware of that.
Okay, actually. So you should just look at some of his papers on the archive.
Weinberg.
Stephen Weinberg.
D. Weinberg.
Steve Weinberg. That's it. And then I mean, but I think I think he still has the positivity, but they're more general. So
okay,
you should try to compare, especially the second one, non-symmetric.
Thanks.
Could you make interpretation of the standard picture of decoherence in your case? I mean that you divide. I mean you define a system, you define environment, and then you trace over irrelevant. I mean environmental degrees of freedom, and your departure from unitarity is because of the lack of the knowledge about the environment. I mean, can you interpret?
Well, the picture here is in some way it's gravity that's providing this environment.
But do you
see?
Yeah.
Because if you switch off it,
do you have some sort of horizon here, for example, which?
Horizon, not really.
Okay, so if you would consider not only the particle which is coupled to gravity, but the whole system, which is the particle together with
plus
the gravity, the total evolution would be still a unitary.
That's what I feel the picture is. But actually, you should work to see the actual unitarity. You should work out the finite form of these transformations and see what is really happening when you're, taking the adjoint of these finite operators.
But do you have a feeling that still, I mean, it's possible in this picture where you have your momentum space curved that for having non-unitary evolution, you don't need any environment for that. I mean, you can have only a system without environment, and only within this system, without lacking of information, you might generate some non-unitary evolution.
I wouldn't say non-unitary. It's more like you actually map pure states into mixed states within a well-defined mathematical framework and within a well-defined model. This is the Tomislav. Yeah. Tomislav. Ah, no. Lugierski. No. No, sorry.
So it was a nice talk. I have two comments. One is the following, that we are using the so-called classical basis for this kappa Poincare. And this is a nice basis from mathematical reasons. But physically, for example, you get quite crazy additional law of energy. So yes. The point is, can you go to other bases which are from other reasons physically?
So you're a connoisseur. The most known basis is a Bicross product, right?
Yeah, okay.
The most worked out.
But
in that case, you know that the coproduct and the antibode are trivial for P0, for the time translation generator. So you would have just ordinary time evolution, for example, in that basis. So you have to look for bases which have non-trivial coproduct and antibode for the time translation.
No, I mean, if you have everything okay in classical basis, that should work also in other bases. I mean, so it's because this is just a change of variables. So I think
but it is a change of variable which trivializes the coproduct antibody for the time transition.
So your statement is that physically, I mean, energy is well described in a classical basis for kappa Poincare. What is phenomenologically quite strong statement.
In principle, this is a falsifiable statement, because if you go ahead and look at that, there is no departures from this thing.
I have another comment. I mean, this is to all people who are doing this curved momentum space. I think the quantum gravity effect, which were reflected in curved momentum space, is the idea of Shan Majid. And I think you should just not forget about it.
Okay, next time I will mention also Shan Majid. Please.
Am I to think about four-dimensional point objects as global monopoles?
Very nice question. So, in fact, in the 3D case, these objects are just vortices, if you think about it, right?
Yeah.
There's been some discussion with Professor Kowalski here on your right about interpreting this 4D example as Taub-NUT spaces. So you have like this gravitational Dirac string, the Misner string.
Yeah,
so it's like a monopole with a string attached.
Okay, but the global monopole is exactly sort of an object you want. It has actually solid angle deficit.
Mm-hmm. Yeah, in fact,
is it what you want?
Well, the Taub-NUT solution is exactly of this type.
Okay.
So you have this monopole with a string attached.
Okay.
And it's, but it's not clear the actual precise mathematical relation.
Okay, and the second question, I mean, this loss of unitarity, am I to connect with the event when 2-point masses touch each other and then the evolution is not determined afterwards? I mean, if they just go through each other, because these are singular points of the manifold, and it's not clear what happens.
So you're talking about vortex...
touching each other, right? They're singular points, and then maybe there is...
where the non-unitarity could kick in?
Yeah.
That I don't know.
Okay.
Because interactions are quite non-trivial in this. Kowalski.
I would like to ask you the same question I always ask you on this occasion. The point is that, of course, if you expand in kappa the equation that you get for rho, you see something which reminds the Lynnwood equation. Mm-hmm. But the question is, in fact, what you start with is a perfectly unitary evolution, right? Because you just use the adjoint action.
No, we don't know. I mean, because
and define the evolution of rho. So at the end of the day, what's your take? Is this equation that you derive, is this expression of the unitary evolution, albeit in some funny form, or does it really reflect the fact that unitarity is non-trivially violated?
No. My take is that should be actually carefully looked at. Is that these things are just unitary representations of these deformed algebra of translations. Just in which way you define unitarity for these non-trivial algebras is a question. Yeah, I asked to people that actually did this and say, what do you mean by unitary representation? And they could not answer. They started talking about star structures and stuff. So physically speaking, mathematically speaking, they know what unitary representation of this object, but physically speaking, it's still a mystery. It's still a mystery. But it should be some kind of weird way of realizing unitarity.